So yesterday we talked about doing something practical, how to deal with competition. Where's my Moore's Law friend?
Here.
Dude, you upgraded yourself, that's right. You're getting very serious about science, that's all right. Okay, anyway, today we're going to talk about something that's totally useless. But it's a lot of fun. It's a lot of fun. We've had a lot of fun working on this problem. And it seems like there are things that you never expect that happen, which is emergent. And so that will be the focus. Again, I said this yesterday, the intention is not to get through my slides. Right? So you want to keep yourself awake. And so the intention is to have a good interactive session. So ask questions if you have any. And I may or may not know the answers, we'll talk about it. So the focus was going to be this business, emergent behavior. And emergent behavior is something that we will, as we go through, we will talk about. The reason we call it polar vortices was these are materials which are fundamentally polar. They're magnet, for example. And there are vortices in them. But also happens to be a real polar vortex. This is 2014. There was a huge mass of cold air that came from all the way from the Arctic. Arctic is right there. To give you a frame of reference, that's Cuba, somewhere here. Washington, D.C. is right out there. Now this is called the real polar vortex. What we're looking at is atomic scale, nanoscale, chicken version of the polar vortex. But these wind patterns are rotating about this way and they rotate about this way. And so we're going to spend some time today looking at how these emerge. And so one of the big things we will talk about today is curls of some things. And in ferroelectricity, unlike in magnetism, our magnetism colleagues live and die. Where's Jean-Marie? Yes. Ah, yes. Yeah. Our Professor Faird gave a talk once when I was at Oak Ridge, and he gave a Wigner lecture. He didn't have one cross product, but he had 3 cross products. Cross. So your mind will start to spin. Ferroelectricity, we don't do as much, but in this talk you will see a lot of cross products. Okay. There are a few people who have been immensely valuable. These 2 guys, both Jorge and Javier, done some fantastic work in terms of doing ab initio, first principles, and now more second principles, where you can, and I'll show you some data on that. We do quite a bit of this work at the light source, and you will see the data. This guy, who was a former student of mine, now he's a staff scientist there. He did quite a bit of work there. And what else? Jim Scott is a big advisor for us. We've been having a lot of fun talking to Jim and a bunch of people. Okay, so that's kind of a quick introduction. What we will talk about is, to begin with, the physics of polar vortices. Why do these things form? Pavel, who's chickened out, he's gone home. And so Pavel started talking about it, but he didn't really get into it. He talked about negative capacitance. We will end up with negative capacitance in this presentation as well. So we're going to spend quite a bit of time looking at the vortices. What can I say about these vortices without worrying about being practical? Then I want to talk about 2 things. One is emergent behavior. Colossal magnetoresistance people talk about as emergent behavior. Mobs are emergent behavior. One human being generally is quite sane. You put 1 million of them together and put some crazy cause, they start to have emergent behavior. So birds flying together is emergent behavior. So we're going to talk about emergent, meaning that the parent things will not have those behaviors. You put them together in a certain way, they start to have behavior that's very different. And then we're going to talk about this business of colossal magnetoresistance, which I was involved with 25 years ago, 30 years ago now, and to see how can we understand large responses. Okay, so let's begin again with the magnetism analog. If you're into skyrmions and stuff like that, this is a nice paper. There's a whole bunch of fantastic work, and it's very difficult to go in and cite all of them. But this paper actually talks about, how you can you can think about the formation of the spin textures. Those are shown here. If you look at them, the Hamiltonian for that looks very similar to some terms. Of course, the various terms have different magnitudes, and therefore they can move things up and down. And so you have a magnetic stiffness term, there's a gradient term, and then very important for these systems is something that breaks inversion symmetry, and this is helped by the Dalechinsky-Moria coupling. And that leads to a handed behavior. And we're going to talk about handedness quite a bit in our discussion today. With ferroelectrics, of course, I don't need a Dalechinsky-Moria because we have inherently something that's broken inversions. So one of the questions has been, can we do the same thing in ferroelectrics? As a matter of fact, in 2004, Laurent Belache published a Nature paper which talked about this, and I'll show you his data in a second. I don't think many people paid attention. About the same time, Matt Dauber published, and Jean-Marc published a very interesting Nature paper, which I reviewed, by the way, which said, hey, look, if I have lead titanate, strontium titanate superanalysis, we start to see improper ferroelectricity. And they were talking about what happens in the strontium titanate. And so we're going to look at the entire spectrum of behavior and say, how does this thing evolve? And it evolves in a very graceful way. Coming back to the textures, the question was, can you form these kinds of dipolar textures, like spin textures? And the other question has always been, if you look at the ferroelectrics community versus the magnetism community, there are two extreme cases. In the case of magnetism, typically, unless you go to very hard ferromagnets like neodymium-ion boron or samarium cobalt ferromagnets, typically ferromagnets are dominated by exchange interaction. You take a piece of iron, the exchange interaction is very strong. The anisotropy terms in ferromagnets typically is lower. And therefore, all the behavior, the switching behavior, the nature of the domain walls are all governed by exchange interaction. So the domain wall width in a piece of a ferromagnet like iron is very large, maybe a few hundred angstroms. In contrast, ferroelectrics, general ferroelectrics, and we're talking about things like lead titanate, are the other end of the spectrum, where the anisotropy in the crystal is much larger. Tom, until I fell asleep, Tom was talking about this morning. The anisotropy in a ferroelectric crystal can be of the order of 4%. That's huge compared to a ferromagnet. And therefore, the domain walls are very thin in a ferromagnet, typically a few unit cells wide. And their switching typically is also different. In the case of a ferromagnet, the spins would actually rotate, which is how magnetic switching happens. Okay. In the case of ferroelectrics, like lead titanate, people always believe that it went through this so-called Vanderbilt mechanism. David Vanderbilt proposed this in the 1990s. The idea was, if this is my dipole pointing up, and on this side it's pointing down, it didn't rotate the dipole because I have a huge penalty from anisotropy. Instead, what it did was to reduce the magnitude of the dipole. I have that flexibility to keep on changing the magnitude. And then it goes to zero, goes to the parent phase, the high temperature phase, and then it switches the direction of the polarization. In yesterday's discussion, if any of you guys remember, yesterday we talked about bismuth ferrite already being very different. Bismuth ferrite did not switch by the classical Vanderbilt mechanism. Instead, it switched by rotating the polarization in two steps. That's what Jorge pointed out when we wrote that paper. Jorge was the guy who said, guys, it may be very different. And indeed it's true, and we can measure it. Therefore, bismuth ferrite, which has a very large structural anisotropy, still behaves like a ferromagnet. So these gaps between the ferroelectrics community and the ferromagnetics community are kind of closing. And Jim Scott was the guy who was saying, we always are programmed to think that these are two different things. Maybe not. Maybe they're looking more and more similar. That's kind of a very long-winded explanation of how these two communities are kind of crisscrossing each other. So the question was, can you form these kinds of textures, but in the charged domain? Okay, so this we should not spend much time. You guys have had enough introduction. We're going to talk about this entire energy landscape in great detail. So instead, I'm going to spend a little bit more time. I thought Pablo was going to set this up, but he went almost there, but he didn't set it up. Okay. So this slide has two parts to it. First part is on the left side, which says, instead of having an infinite crystal where I don't have any boundary conditions, if I now make a finite crystal, how does that crystal accommodate its boundary conditions? And what are the terms that impact the boundary condition? If this is now a crystal sitting on a substrate, which most of us work with, if it's just a freestanding crystal, the mechanical boundary conditions are different. So in our case, we have four terms that contribute to the Hamiltonian of the system, the free energy of the system. One is, of course, the Landau free energy, that bulk. There is a gradient energy. In all of these terms, you always see the gradient term, because you're going to be putting in domain walls where the polarization is changing directions. But in the case of a material that's stuck to a substrate, which has a very different structural and mechanical properties, you have an elastic energy. And this is going to be a very important player in our discussion today. And then, of course, there's an electrostatic energy. And that's what you play with. And if you go through the process, in a classical macroscopic system, you will see that it forms domains like this. These are very classical, and in this case, these are 180-degree domains, polarization up and down. This is a tetragonal material. Remember, Tom was talking about symmetry. Symmetry is very important. You cannot cheat on symmetry, especially in ferroelectrics, because the polarization vector cannot deviate too much from those axes. So here it is going along the 001 and 00 minus 1. And these are 90-degree domains because you can now put the c-axis this way, and this way. So you have all the symmetry operators that are used. This is very classical. We're not interested in this. This is very trivial. We're not interested in this. Now, this was the paper I was talking about from Laurent Delage. They were like speculating. They were doing theory, ab initio theory. They said, look, if I had a narrow disk of PCT, which is a canonical material, instead of forming these kinds of structures, I would now have something that looks like a vortex. And not many people paid attention to it. As a matter of fact, we were not paying attention either. We had no interest at all in all of these kinds of structures. And I will tell you in about half an hour, I'll tell you what we were really interested in. And we then saw some things in our early work, and we have not gone back to the thing that was so interesting to us in the first place. Okay, so this was theoretically predicted, but for about 8 years or 10 years, nobody really reported anything from this. So that brings us to the framework for our discussion today, which says, okay, if I have a polar material, in our case it's lead titanate is a model system, which is this layer. These are atomic resolution images of a superlattice. I can now start to impose boundary conditions. If you remember, we talked about these boundary conditions. I can systematically tune these. So I can say, I can put a polar gradient by simply going across lead titanate to strontium titanate. I put a polarization gradient. That's the first thing. I can put elastic gradients. I can change the compliance tensor for the two materials. I can put a gradient in the elastic properties. In the same way, I can put dielectric gradients. I can change the Landau potential. Of course, this is directly impacting here. So I can do a lot of things. That is just within a material that's polar. Lead titanate, strontium titanate. Lead titanate, barium titanate. Now I can introduce other degrees of freedom. I can go into the spin and the orbital degrees of freedom in other perovskites. And I can start to build up this structure. That's where we're going to end up. At the end of our discussion, we're going to say, what else can we do? Okay. So this gives you the framework for how to think about these kinds of things. With all of the techniques that we have today, and that brings us to this slide, which is really very important. Now, everything that I showed you here is atomically terminated, meaning that I can go from within 1 unit cell, 4 angstroms, I can go from lead titanate to strontium titanate. Which really means you need to have the control in the synthesis part of it to be able to say that. Okay. That's not trivial, which really means it has to look and feel like a molecular beam epitaxy process, where I can put layer by layer. I put a titanium dioxide layer, go in and put a lead oxide. Titanium dioxide, strontium oxide. That level of control needs to happen. And with techniques like MBE, Darrow Sloan, There are other people around the world who do MBE, real MBE, with K cells and stuff like that. We do the poor man's version of MBE. We do something called laser MBE, which is a pulse laser deposition process, which is coupled with ultra-high vacuum read, which is electron diffraction, surface diffraction. And so you can follow the growth of this layer by layer process by looking at the oscillations of the reflex. This is very important because in order to get a structure like this, I have to avoid chemistry. I have to avoid interdiffusion. Interdiffusion, chemical energy scales are much larger than all these other energies that we talked about. So you would not see any of these effects if you had a layer that's interdiffused. Okay. So these oscillations are telling you that the material is indeed growing unit cell by unit cell, layer by layer. It wasn't very easy for us to get to this. But it turns out that if I grow lead titanate from a pure lead titanate target, you will have so much of desorption of lead from the surface that the system automatically will go into island growth, which is shown here, or 3D growth. In order to sustain the layer by layer growth, you need to have excess lead in the system. That was kind of an interesting learning for somebody like myself. You need to have about 20% excess lead. That's what we used for our process. With that, you could see these kind of read oscillations all the way to the growth of 200 nanometer thick superlattices. So the system is very stable. So this is not necessarily a trivial process to grow, but once you have the recipe, then you can start to do it quite well. And with lead titanate, strontium titanate, we can do it we meaning the community can do it very well. Other people do it as well. Okay, and when you grow these kinds of structures, that's what you see. This is just a regular electron microscope image of the superlattice. This is a 10 unit cell by 10 unit cell superlattice. The white layers are lead titanate, and the dark layers are strontium titanate. I'm going to go deep into this in the next few slides, so we will see a lot of electron microscopy data. X-ray diffraction, this looks pretty standard. You can see very clearly the superlattice peaks. And you can see also those oscillations, which is telling you that these layers are very coherent. They're not interdiffusing. Already it's telling you something is very, very high quality. When you do reciprocal space map, you can look at the correlations in reciprocal space. What we saw, of course, there's a lot of detail here which tells you about the structure, but there was a few things that we saw which were very unique, which nobody had reported before. These streak-like things. They suggested something with the periodicity of about a few nanometers, 9 to 10 nanometers. Okay. We are essentially going to talk about this structure for the rest of the talk. We're only going to focus on this stuff. Yes?
Excuse me. On the previous slide, you show your read oscillation. It seems that it improves each two B layers. An explanation?
It's a really good question. I'm not sure if it is something routine, or if it is a meaning that is very controllable. I had the same question too. Is it something that's happening on an ordered basis, or is it a statistical? We haven't seen this again and again and again to be able to say, oh look, something is correlated. Okay, so we're going to focus on these streaks. What do those say in reciprocal space and in real space? Okay, so then we have some fantastic capabilities. Many labs have this now. Berkeley has the National Center for Electron Microscopy, and we have the aberration-corrected electron microscope. The resolution for this microscope is half an angstrom. So in principle, you could see the atomic structure of essentially any material. So what Chris did was to take the sample and then just do atomic resolution imaging. Now I'm not showing you the actual images, but I'm just showing you the outcome. So what does this entail? You take this and look at the atomic structure. You look at the high resolution image. These are STEM images. And this is a strontium titanate layer, and we're going to get to this lead titanate layer. Then you take that information, it's a map of intensity distribution. You take that and put it into a computer and ask the computer to do an analysis. So for that, let's use the chalkboard if you guys can see it, because I should have had a slide which I did. So these patterns look like
Okay.
Okay. That's fine, that's fine. No, this is only for 2 minutes, guys. I should have had this slide, but... So what you have is a pattern that looks like this. Very standard graphs that what Tom talked about this morning. You have a pattern of 4 large dots, which are really the lead atoms. The scales with the 4th power approximately of the atomic number. Sorry, 2nd power. The 4th power is something else. There's an order coupling. This is 2nd power of the atomic number. These are the lead and the titanium. Then you can ask the computer to do a thinking process. Say, hey, look, tell me how this atom is moving with respect to this pattern of 4. And you can ask it to go across the unit cell, across the image, and ask, what does it do here? And what does it do here? And so on and so forth. If it was a pure ferroelectric, you would simply see what Tom was talking about. You would see this shift up. You would see this. You don't see that in our image. So let's now turn off the light.
That's one.
Left, right, symmetric problems. I've had all through my life left, right. Anyway, so what we see instead is something that looks very fascinating. Very fascinating. You see these vortex-like structures. Okay, very ordered, and I'm going to show you a whole bunch of authentication to show what this is. Very ordered structures. And you can see this, one of them is blown up here. The dipoles in one of the vortices, and the physicists will get very mad. We call them a vortex and an anti-vortex because they're rotating in opposite directions. They have totally different connotation if you're costalids and costalids and others. Okay, they're talking about superconductivity, very different. But for just simplicity, we're calling this a vortex. This is an anti-vortex. Okay, they're rotating opposites. There's a lot of things that we're going to dive deep into in terms of the properties of these vortices and anti-vortices. These are phase field calculations, and I will show you in just a few seconds. Ab initio calculations from Javier and Jorge. They all seem to agree quite a bit. These are basically telling you, indeed, that the polarization is rotating continuously. So one of the questions, and we talked about this in the introduction, we said, okay, how do I look at this? One way is to ask the question, what does the curl of the polarization look like? If I have a uniform polarization, what should the curl of the polarization look like?
Is it 0?
0. There should be no curl because the polarization is just uniform. If I did that, this is done in the computer, you can clearly see that the polarization is indeed curving. So one of the signatures of this kind of a vortex structure is that there is a finite value of the curl everywhere in the sample. You can understand this, and I'm not going to go into it because it's a lot of mathematical mumbo jumbo. You can understand the formation of these kinds of vortices by using Stokes' equation as well. Okay. We will not do that here because we should go on to look at the properties of these vortices. So the first thing you can say is that these things form some very interesting. Yeah.
Excuse me.
Yeah.
What about the dipoles perpendicular?
Vincent just went about 10 steps ahead. So this is essentially, so again, we will use our time-trusted Bollywood analogy. Right? In Bollywood movies, there's always one of those scenes where something evil happens or something dramatic happens. Vincent's question was essentially the crux of this problem. And we're going to come to it. The question he's asking is, what happens to the polarization, if any, in and out of the plane? And essentially the entire story, if I told you the answer to that, it's like cutting off a Bollywood movie at the interval. You can't get your popcorn and go back anymore. That's not allowed, that's illegal. So those conditions are not good. Okay, so I will come back to it in a second. So the first thing you can see is this is a 2D section. That's why he was asking the question. And because you're dealing with mechanics, you have to be very careful about this. Why? Because I went from quote-unquote macroscopic sample. This was a 5 by 5 millimeter sample. I took it and I sliced it so that in this dimension it's only 10 to 20 nanometers. It's electron transparent. But in doing that, I've entirely changed the mechanics of the sample. And if you remember that Hamiltonian we wrote down, it had a mechanical component. And so my first question was, oh, this may be something to do with sample preparation. And it turns out it's not. I will show you later. Okay. Now, the next thing we did was, oh, this is too fancy. You know, when you get all these computers involved and you're doing all the analysis, I get very suspicious because I'm a little bit old-fashioned. We said, let's go back to conventional microscopy. So I'm going to show you some data. This is looking at exactly the same structure, but not with high-resolution microscopy, but just by diffraction contrast. And you can see the vortex structures. They don't have a difference in contrast because you're just picking up the distortions in the phase. But you can see the ordering of the vortices this way, and reasonably ordered this way. Not completely ordered vertically, but ordered in this way. And you can see that by the superlattice piece. If I now look at this from the top, you see something that we have never seen before in lead titanate. Lead titanate will typically give you nice ferroelectric domains. We don't see that. What we see instead are these long fringe-like contrasts. And again, you could say, oh, look, you changed your mechanical boundary conditions. How do you know this is representative of the sample? One way to look, is this guy. And this is why I was making such a big deal out of it. These guys are essentially the same as this spacing. It's picking up those. So you could see that there are regions which is oscillating, high intensity, low intensity. We're going to get back to it in a second. That spacing is about 10 nanometers. That's approximately the vortex, anti-vortex, vortex spacing. Okay. So from the top, it looks very different. Now you can see there's contrast here, and for a while we didn't understand what those were, and we just figured out what they are, and I'll come back to it at the end of my presentation. You can look at structures. This is now a tri-layer structure. We simplified our superlattice by just growing 3 layers. Strontium titanate, lead titanate, strontium titanate. In this case, it's a 10 by 10 kind of superlattice. And you could see these boundaries very well. These are the same boundaries as these guys, but much well defined. And these look like antiphase domain boundaries, where from this side to this side, there's a shift of lambda by 2 of the vortex structure. Remember, there's a vortex, anti-vortex, vortex. You can shift them by half a wave. So that's what these boundaries are. And we're going to come back to it in a few minutes to understand what they do. It is very clear from piezo force microscopy. Alexei will talk about the imaging process next week. But from piezo force microscopy, you can see that the polarization, there's an in-plane polarization component in these guys, is changing by 180 degrees. It's going from this to this. We'll come back to it later. Okay, so let's capture this, and we'll get back to Vincent's question in the next segment. So what we can say for sure now is that for certain dimensions of these superlattices, of the strontium titanate and lead titanate layers, you do form this vortex-like structure. That's the calculation, that's the experimental image, that's the energy distribution. These are very different from the classical domain wall structures. If I now coarsen my superlattice, this is a much thicker, this is about 15, 20 nanometer thick lead titanate layer, these now become classical. I'm not interested in this at all, because they form 90 degree domains and 180 degree domains. I'm not very interested in those. We're interested in the case where the curl of P is not 0 anywhere. Then we're going to ask the question, so what if the curl of P is not 0 anywhere? What do I get from that? Okay. So that's kind of the first order summary. Now, this slide is important. I'm going to let it play. It's kind of a movie. It's a movie based on just calculation. So before I put it back on, I should tell you what we did. Basically, you can do the phase field calculation. You can take the crystal as a computer, and you cool it down to below the transition temperature. And you can take snapshots of this, approximately 40, 50 femtosecond time constant, approximately, because it's not easy to do that. And so what you're going to see is there's the superlattice, which is lead titanate and strontium titanate. But as soon as I cool it down, let me go back again. As soon as I cool it down, this layer will become red in the plane. Dipoling fields, which is very electronic in nature, says, hey, look, you're giving me 100 microcoulombs per centimeter squared, approximately 80, so the real number. and it says, put the polarization in plane. And so the system, first order, puts the polarization in plane. Okay. But then it says, oh, I have a problem. It's scratching its head and saying, oh, I have a problem, because in putting the polarization in plane, I've also put a few % strain in plane, because the polarization and the spontaneous distortion go hand in hand. So let's go back to it. So it's doing it already in a loop, so we can talk about this. So the system then says, oh, I have to worry about the strain that I've created. But then to accommodate the strain, I have to do something. It's not an electronic phenomenon. It involves the lattice. Okay? So what you'll see in this set of calculations, we haven't done this experiment yet, is that you will see the nucleation of the vortex there. But if I put my marker there, that point never moves in the sample. It simply stays there. So one way to think about this is that you have this sheet of lead titanate with the polarization vector in plane. And there's a strain. And therefore, you can accommodate the strain by doing many things. We think it does by putting in a strain wave. We think it doesn't put a traveling wave, it puts a stationary wave. And indeed, this is what we were looking for. We don't have experimental evidence for this. The grand challenge, unlike electronics, is in phonons is, can you localize a phonon? And this is something we're going to come back to at the end. Phonons behave very differently. They're bosons, while electrons are fermions. They have different statistics. How does it influence the behavior of the phonon when I confine it? So the question that we were asking is, about 25 years ago, there are people who predicted that in superlattices, you should start to see a change in behavior from a particle, which is typically how people think of phonons, to coherent transport behavior, where it behaves like a wave. That approximately happens near the mean free path for phonons. And for these oxides, the mean free path is about 3 to 4 unit cells of the order, maybe 5 unit cells. So our interest was, we had published a paper about 5 years ago, where we said that in barium titanate, strontium titanate superlattices, we could see a thickness dependence of the thermal conductivity. And that's how you would understand phonon behavior, do thermal conductivity measurements. And because there are no electrons in the system, I'm simply looking at the phonon contribution to the thermal conductivity. So we saw a minimum. We didn't see a dramatic minimum. We saw a minimum. We saw, oh, UP hooray. So we wanted to go in and change the acoustic contrast between the two layers, which is why we went from strontium titanate to lead titanate. And we did not expect that vortices like these would form. But one of the things we're looking for is whether the strain wave is a stationary wave that goes through the lead titanate layer and then subsequently forms the vortex afterwards. Keep in mind that there is a time difference between this process, which happens essentially instantaneously, and when the phonons can anybody take a guess as to what that time constant should be for this strain wave? If you had to go back to one textbook, what would be the approximate time constant for the strain wave to go through? Huh? Sorry, louder. Old people here can't hear very well. Take a guess. It's okay. I don't want you guys to feel shy about it. I'm going to take a guess because I don't know the answer either. Yes? What do you think is, so let's ask this question. What's the fastest velocity of a domain wall in a ferrovector? Huh? Sound wave, yes, acoustic phonon mode, right? We're not talking about optical phonons here, although they exist. We're talking about acoustic phonons. So the approximate thing, and it's approximately of that order. It happens in a few picoseconds, maybe 10 picoseconds or so. In the computer, we don't know this experimentally. So you can think of the strain wave propagating with something like the acoustic phonon mode, or the velocity of sound. So the reason I make such a big deal out of this slide is because it is a fantastic opportunity for students to go back and do the research. If we can see phonon localization, that's pretty awesome. Nobody has seen it yet. And we think we see this God, but it's not there yet. Okay.
Question?
Yes.
What were the boundary conditions in that calculation, because I mean, if you say if it is, it behaves kind of like a standing wave, boundary conditions play a role, and I mean, if it's strain relaxation, you can also think that boundary conditions, if the boundary is free to move, it will play a role and it change the system.
Yeah.
Did you
Yeah,
investigate that?
Of course, of course.
Yeah.
So that particular calculation was for literally the same sample that we grew experimentally. So the substrate, perhaps that's a good point. The substrates that we use for almost all these studies you will see today is dysprosium scandate. Dysprosium scandate is not a square surface, it's a little bit of a tetragonal, rectangular surface. And that's what the calculation was for. And it used the elastic constants for lead titanate, strontium titanate, which are pretty well known. It used the polarization, spontaneous polarization for those two materials from published literature, which is relatively well known. So we didn't impose any additional boundary conditions other than the ones that I showed you in our original Hamiltonian. There's clearly the Landau free energy, there's a gradient term, there's an elastic energy term. The elastic energy term comes from the fact that ideally you want to put the polarization in plane. That way I have no dipoling fields. But then you pay the penalty of the elastic energy, right? Or if I were to optimize only elastic energy, then I would put the polarization out of plane so it's all lined up. Then I have 100 microcoulombs of dipoling energy. But for certain periodicities, those two things are approximately the same, which is why you see these vortices. Okay, so the boundary conditions. Yes?
An additional question.
Yeah.
So if I understood well, this process takes place during the cooling process
Yes.
from the paraelectric to the ferroelectric.
Yes.
So what happens if you grow your material in the ferroelectric?
That's a good question. That's right. So we can do that with bismuth ferrite.
Yeah.
We can't, and I'll show you at the end what happens with bismuth ferrite is something that we never expected. That'll be the last 5 minutes of my presentation. This is very interesting. It's not something that you would say is very obvious. It's emergent, but in a very different way. With lead titanate, of course, our TC is much lower. It's only about 450, 490 degrees centigrade. We grow this at 650 degrees centigrade, so it's difficult. But that's a really good question. What happens if I now grow it into the polar phase? Okay, so yesterday Pavel talked about a little bit about this, about what happens with the STO thickness. We have mapped out, at least theoretically, with phase field modeling, the dependence on the strontium titanate layer thickness. And you can see that when the strontium titanate is only a few unit cells, let's say up to 5 unit cells, the presence of lead titanate on either side polarizes strontium titanate. It becomes ferroelectric, which is exactly what Matt Dauber and Jean-Marc had seen 10, 12 years ago. And they were saying that the strontium titanate became an improper ferroelectric because of the tilts that were coming in. We think that's exactly what happens here. But as I make it thicker and thicker, somewhere here we have a vortex plus other mixed phases. Then when you make it very thick, it simply becomes in-plane polarized. Okay, so there's a good phase evolution for the system as a function of the dimensions. So evolution of the vortex state, we think that this is decoupling the charge effects, the dipoling field effects, and the strain effects, and the elastic effects. There's a finite time, it's about 3 orders of magnitude slower. In the computer, we don't have any measurements here. It looks like a strange spinodal. How many of you guys have not heard of a spinodal? Okay, all right, so let me just, we'll come back to this in a different connotation. We should just at least draw the free energy functional to say what the spinodal means. Physics community does not talk about this. This is a shame because physics is very focused on electronic structure. It doesn't go away from electrons. If it's not electrons, it's not working. And actually, it's very important here to look at. So, if I look at simple systems, the classical system is something that flies on your plane. Every rivet in your plane is an aluminum copper system. And unfortunately, you guys are all too young to have heard this term, the Guinea-Preston zones. These are very small precipitates, they're tens of angstrom sized precipitates. And when they form in the aluminum copper alloy, they harden the alloy. Aluminum is a very soft material. Ideally, you would not think of using aluminum, except for interconnects in chips, for an aircraft. But when you do the thermal treatment right, you have a spinodal decomposition. So the question is, what is a spinodal? Okay. So if my composition is easier, if I'm now sitting somewhere here, this is the free energy curve, right? And there are points within which the curvature, the second derivative, is negative. Which means, if I'm sitting here, the system spontaneously goes into two phases. It'll start rolling down the hill. To here and here. There are no barriers. Unlike a classical process where, any phase transformation, you have to nucleate and grow. There are no barriers. And it'll have multiple wavelengths, but we'll pick one wavelength at a time. And so in the aluminum copper system, it has a chemical spinodal. You have chemical decomposition. This is why composition is the order parameter. Now, what we think is going on is it's not in chemical space, but I can actually have a similar phase diagram in strain space. So it's getting fluctuations in strain, in the lattice strain, and that then forms this strain wave, and then leads to the formation of the vortex. All right, so that's kind of the summary. If you're interested in strain spinodals, this is a good Robin Rudensma and Andy Zhang wrote a very nice article. This is already 30 years ago. You should check it out. Okay, so for the next few minutes, we're going to now say, okay, what can I say about this vortex? I'm going to show you one small example and one really fantastic example, which will take some time. So the first thing that we can do is, I can take this vortex and I can go say, can I go measure something within the vortex? I'm going to now show you results from electron microscopy. Somebody talked about this yesterday, and I'm forgetting who it was. It's not good. Oh, Albina talked about this yesterday. She was talking about new kinds of sources. You can have, typically the electron beam in a microscope is a parallel beam, but there's nothing that says I cannot make it a spiral beam. You can put zone plates, like they do here, and create a spiral beam. And this paper, this is one of the papers, and the Schatzsnyder paper was a similar paper, where you can now, like you would do with X-rays, circularly polarized X-rays, you could also have circularly polarized electron beams. And you can do circular dipole measurements. The absorption of light, in this case electrons, in a ferromagnetic material would be different depending on the helicity, whether it's going this way or this way. And that's what this experiment is. And the difference between them is a dipole. And typically in a system that breaks time symmetry, a ferromagnet, for example, will show this difference. And in X-rays, that would be called X-ray magnetic circular dipoles, because it's magnetic in origin. In electrons, it would be electron magnetic circular dipoles. So David Mueller, who's bar none really good microscopist, so I'm going to show you data from our work with him. So we said, okay, people use all of these fancy things to create a helical beam. We already have a helical sample. Why can't I look at the helical sample and use a boring beam, a fancy beam and boring detector? What if we flip it and get a very boring beam, but the sample itself has all the fancy stuff? So what you can extract from this is shown in this simple equation, but basically, let me put it into English. Okay, so I can have, I'm a stupid experimentalist, so for us, all of these things looks pretty heavy. So when you get into triple cross products, we start to shake. Okay. Anyway, so what you can do is, let's say I'm an electron. Let's go back to our picture. I'm an electron going through this, and I look at the polarization. What can I extract from this? So in some sense, I'm going to show you data, and then we'll finish up again. Show you data which talks about how I can use to do electron-based photography of the dipole. And ask the question, what does this electron experience? Okay. So basically you can say, what is the angular momentum that's imparted to the electron? The electron is going through the sample, but the sample itself is rotating like this, or the dipoles are rotating. What does that do to the angular momentum of the electron? So in some sense, I can map out what happened in the sample by looking at what happened to the electron. So at the end of the day, you get a torque that's imparted to the electron. The electron is being rotated. That's the time derivative of the angular momentum, basically. This is just from our mechanics classes. And you get all of that from the wave function, etc. And this, to extract all of this, you have to do something called the tychography, which I will not go into the details. I'll ask you to go back and look at David's work. There's a whole bunch of people working on this. But this integrated through the sample, this electron beam takes a finite time to go through the sample of about 10 nanometers, gives me the total torque, and therefore gives me the total angular momentum. So that's the experiment that David and Kyla did. And what you see here is indeed, this is the vortex-like structure, and you can actually see that there are regions which have positive torque, and there are regions which have negative torque. And you can also see this scaling. We think this is real and it's important. And it's part of the answer to Vincent's question that something is breaking symmetry here already. So if I were to dream, I would say, okay, perhaps it doesn't have a mirror symmetry again. We're going to come back to the mirror symmetry question again. And so the second part of this is that this is quantized in terms, I shouldn't say quantized, that's too strong a word. It is in units of h bar. It goes from plus or minus h bar by 2. We have no clue what this means, whether it means anything dramatic. We're still scratching our head, which is why all of this has not been published here. We're trying to figure out, is this some quantum behavior, or is it just accidental for the sample that it was h bar? That's the typical number. Okay, so the key thing I want you to take away is I can now start to go within a unit cell. The electron beam gives us an angstrom field. I can go into the sample and probe what happens. So the other thing that we could do, and I'll show you that as the last piece of data in this presentation, you can also go in and do map out the electric field as a function of spatial location. And from the electric field, you can work backwards. You can get the potential energy landscape across the sample. Okay, so that was a short story. I'm not going to stop and say, okay, we see something very interesting within the vortex. What happens across the vortices? So the data you're going to see, in my mind, is spectacular data, and I'll take you through this whole set of experiments. So what we were interested in is these vortices, and this was going to hopefully answer Vincent's question. Do these vortices have a sense of handedness? Now, in condensed matter, topology is a big deal. You don't want to mess around with that because this is really deep physics. Chirality in condensed matter is also very, very deep. So if you don't want to get into it, you shouldn't get into it. Because the condensed matter physics will beat you, guys will beat you up on this. So we were saying, okay, is there a handedness? Because one of them is rotating this way. The other is rotating this way. Okay. But for it to have handedness, like us, it has to have other attributes. So we're saying, how do I understand the emergence, possible emergence of handed behavior? Okay. What are the features required? What Vincent pointed out is perhaps the most important feature. I'm going to show you data for that. Okay, so you can see all of these virus-like structures. By the way, side question. The human system, can it take L-glucose? Huh? If I gave you L-glucose, what happens to you? If I gave you D-glucose, I think some of us will need D-glucose after this entire workshop. But what happens if I give you L-glucose? Huh? The human system will not assimilate L-glucose. So this is still, I mean, there's a lot of theories on this. The human system will just, some people can just have shock, or you'll just carry it away. It'll be like a piece of sand or something. We cannot assimilate L-glucose. For that same reason, there's all kinds of theories about, some asymmetry in the universe and stuff. We can only use amino acids which are L. Label, not dextro. So the question we're playing with at this point. Keep in mind, none of this is is we're not going to start a company and make anything, but we're saying, unlike yesterday where it's very serious in that sense, can I have something like D-glucose and L-glucose, but instead can I go back and forth from D-glucose to L-glucose? I can, for example, give you D-glucose, shine a microwave, and it becomes L-glucose, and you go kaboom. Something like that. Okay, that was joking. No harm in that. We're not like that. Got to be very careful. Okay, anyway, so the question was, how do I look for chirality? How do I explain chirality? Or possible chirality? So the technique that we're using, and this is where the fantastic part comes in, is just what X-ray guys can do is just diagram. Right? So the technique that we use, this is a loaded slide, so I'm going to take you through one at a time, is something called resonant soft X-ray diffraction. The soft X-rays, because the wavelengths are typically a few nanometers, unlike copper K alpha is 1.54 angstroms. This is maybe 30 angstroms, soft X-rays. At the light source at Berkeley, we're very well set because that's typically the kind of wavelength scale which we're using soft X-rays. So what I do is to come in with the X-ray beam, and I do diffraction. So if I have a bunch of lines on the surface, right, I can come in and do diffraction. But that's one of the things, that's the first thing I do. I do a soft X-ray diffraction. But then I can switch over to my chemical node. I can go and say, hey, sit at the manganese side, for example, in this case. Sit at a particular absorption edge and do absorption spectroscopy. So that's the second thing you can do. Then the third thing, would you like some water, ma'am?
No, it's
okay. It should be like shocking to you. So the third thing we can do is to look at what happens when I change the helicity of the X-rays. So those are the three things we're doing. So we're looking for element specific, where you can look at the transitions, for example, 3D to P transitions. I can look at orbital effects as well, which people have done in the magnetites. This is not the 113, it's the other magnetite. And so that spacing of the orbitally ordered structure is about 1 nanometer. Very appropriate for soft X-ray diffraction. We talked about X-ray magnetic circular dichroism. That's kind of the example. You look at the absorption. This is just a piece of iron. You have the absorption with left circular depolarized light and the right circular depolarized light. That difference is shown here. That is magnetic circular dichroism. You can integrate that using the so-called spin-sums rule, and you can get the effective moment of the sample. In a piece of iron, it will only be the spin component, but in some cases you will have the orbital. Okay. These guys are the experts that we really work with. So what else can we say about this? Because this is resonant, you have like an amplification factor. And the folks at the diamond source are really the people, Gerrit van der Laan and Steve Lovesey. These guys are amazing in terms of all the early work that was done, all the theory work that was done. So because it's resonant, you can get amplification of the interaction process by 1,000,000 times. So what you will not see in a regular absorption process, the resonant absorption process will show you in great detail. Okay, so people have used this, and this is work from Sven Lagerwall way back in the 80s, to look at chirality in liquid crystals. In the smectic, is there some star, P star, I don't know the language very well, symmetry, C star, one of them is handed, liquid crystal. And so you can look for that by looking at the diffraction peaks with polarization dependence and looking at the W. So you can do these kinds, people have done this kind of experiment for liquid crystals. In some sense, we treat our vortices exactly like liquid crystals. So we have spatial selectivity of the diffraction. If I have a mixed sample, and in our case, I'm going to show you later that it is indeed a mixed sample. It has more than one phase. It doesn't matter because I'm selecting something which is diffracting. And then I'm doing, yes, sorry.
Sorry, I missed the point. XMCD is generally used for ferromagnetic materials.
Yes.
So the point is that you have a gradient of electric field that is equivalent to a magnetic field and that you use.
Exactly. So we're going to come to that as to why XMCD. We don't have any M here. There is no magnetic system here. So I'm so glad Ines brought up this. I kind of No, it's not here. So typically, when you have circular dichroism, the M part is a very specific thing. If I have something that breaks time reversal symmetry, then you have it absorbs circularly polarized light differently, left and right. That's this data. And the question is, what other sources can give rise to circular dichroism? One of them is a handed behavior, and you can think of it exactly the way that Ines was talking about. That there is this a curl of the P that acts like a virtual magnetism. Okay. So the experiments that we've been doing for the last 18 months is still not published because we're slowly sorting through everything, is to look at, this is the sample, that's the top of the sample, the vortices are going in and out of the plane of the board, and they're coming into the X-rays. And we see very clear diffraction from the vortices. This is the first order, and the second order is kind of faint here, and you can see it very clearly here. So what we're going to do now is to sit here or here, and do absorption spectroscopy with left and right circularly polarized light. So you can pick up all of these things. It basically acts like a diffraction gradient. But the fact that it's resonant means it's enhanced. Okay, so this is the same data, just taking a section of this. And this is perhaps the most important piece of data in this entire presentation. Is the red and the blue curves here. And that's the specular reflection -1, -2, +1, +2. Red and the blue curves are with circular positive, circular negative, this way and this way. And you can see that very clearly there's a difference between them. That difference is asymmetric, which again is a signature of a handed behavior. We're going to get to the why handed in a second, which is the answer to Vincent's question. This can be sometimes as large as 30%, typically about 15%. So we have a sample that behaves like a ferromagnet. There is no ferromagnetic species here. So we've got lead, titanium, oxygen, but none of them are ferromagnetic. So the origin of the circular dichroism is coming from something that has behavior like a liquid crystal, or more generally something that is handed crystal. Okay, then you can go a little bit more into the details. We have done the oxygen edge, we've looked at the titanium edge. The first thing you can see, this is again looking at spectroscopic mode now. That's a titanium absorption edge. Titanium has a very classical 4 peak. The T2G and the EG, L2 and L3. So you'll see 4 peaks. The first thing that you see with this resonant absorption experiment is that only one of them, the T2G, is the strongest one. The other 3 peaks are kind of very weak if they're there. Okay. And you can see that there is clear, in this case about 10%, dichroism with left and right circularly polarized light, and it's flipping in sign when you go from the negative diffraction spot to the positive diffraction spot. Okay. So all of these seem to indicate that there is a handed behavior in the process. A few points. When we have samples which have uniform polarization, we call that A1, A2 because the ferroelectric polarization is this way or this way in plane. With uniform polarization, we see no circular dichroism. Indeed, these samples already have, as I'm going to show you in a few minutes, they have a mixture of the uniform polarization and the vortex phase. And it seems like it doesn't even care about the uniform polarization because it is very resonant to that particular spacing of the vortex. That's the first part. Okay. We can also make samples which have the so-called classical Dipoles domains, meaning they have classical 180-degree domains, maybe 10-15 nanometers spaced. They show no circular dichroism. It's only these samples which have the vortex-like structure which show circular dichroism, which is why we were trying to make a big deal about the curl of P. The curl of P is very important in terms of explaining all of this. If the polarization is not continuously rotating, you don't see this. Okay. So this is now the details of this. This is a beautiful picture, so I'll get to that in a second. We have done quite a bit of in-plane measurements. We have some limitations on the experiments, so we can't sample all of the space. But what I can tell you for sure is that it looks approximately like this. It has 2 lobes, and one of the lobes is shown here. The other one is kind of partial because the experimental setup is blocking it. So there are features of the vortex supercell which remain effectively unchanged by a 180 degrees rotation. That's this picture. There's a change in the polarity, positive, negative change for the negative diffraction spot to the positive diffraction spot. And then, perhaps the most important, is there are regions of the sample which show positive 20 to 30%, and then there are regions of the sample which show negative values. So in some sense, I could think of this as a D-glucose part, and think of this as the L-glucose part. Then we did an experiment which, stupidly, we did not do carefully enough. And the reason I say it's not careful is because we didn't have enough beam time. We did not do the image before the switching. So this is essentially a sample like the previous one where we had switched a portion of it. And you could see that what is positive is generally positive here, and it's negative here. A part of this has been switched from bluish, which is negative, and the circle that goes to green and to positive. So in principle, saying that I can take something which has negative chirality and switch it to positive chirality, negative handedness to positive handedness. And we need to go back and do more quantification of this to prove that indeed that's happening. So I could now start to think about using the handedness as an order parameter. In organic chemistry, mixtures of these would be called the racemic mixture. You have the D-glucose and the L-glucose, 50-50 mixtures are called the racemic mixtures. But if I can now selectively switch one from the other, that would be pretty interesting. Okay, so now comes a beautiful piece of work that Javier and Jorge did. So the question is, how does one begin to understand this? And this really is slowly getting to the sense question. If I simply had in 2 dimensions, one rotating this way, one rotating this way, I could put a middle plane in between them. It was very symmetric, 2 things doing this way. I could put a middle plane between them. That would not be handed. So for this to be handed in real 3D terms, and Jiří Hlinka, who's in Prague, he is very insistent that we should be thinking about handedness in 3 dimensions. The community is actually has different opinions about whether it should be 2-dimensional or 3-dimensional. So I'm going to take the Hlinka approach, Jiří Hlinka's approach, and say, how do I prove that this set of vortices has 3-dimensional handedness? Okay. Now it turns out that you can take this and calculate, and this is really work that Javier and Jorge did, and they've been educating us for the last 6 to 8 months, is you can calculate something called the helicity, very similar to what the Skirmion folks would do. Okay. And that's given by the gamma term, that's the helicity parameter. So what he did was the following. In all of their calculations, both phase field and ab initio, when they have vortices like this and this, they always find that there is an in-plane component from calculation. I'm going to show you experimental data in just a second. They always find that there is a component which is coming out, coming out of the plane for this vortex, going into the plane for this vortex. That is truly important because that's what leads to this helicity component. If I didn't have that, this would be 0. And indeed, they have in their calculations, the energy landscape for these kinds of systems, as you would expect, is kind of very complex. It's very much like human systems, very complicated. Okay. So what you can do is, for example, this is one of the set of vortices, and this is the one which is left-handed and right-handed. So you can calculate for this, what does the helicity look like? And that's shown here in the bottom. Okay. For these guys, both of them have negative helicity of -1. And for these guys, it's positive. Although the vortices themselves are doing this and this. And because it's for one of them, there's a component this way, the other one, there's a component this way coming out. So you can think of it in Vincent's question, there is an in-plane ferroelectric component that's anti-parallel to each other. So once you do that, this helicity term becomes a positive or a negative value for both. Perhaps this is the most important slide to explain why we saw this picture. Because if I simply had vortices doing this and this, you would think first order, they would cancel out each other. They don't. They don't cancel out each other because their helicity is added either negatively or positively. So this was the first piece of evidence which clearly said, hey, look, you have a Y component of the polarization. And for us to look for the white component was a sweat job, and we're still sweating on it. I'll show you some data where it seems like, okay, we can measure it with electron microscopy, but it's not trivial. You have to be really careful about it. Okay, any questions on this? This, in my mind, the circular dichroism data was staggering. We did not expect it at all. That shows that something emergent was happening. And how Javier and Jorge were able to explain this was equally fantastic to me, that they said, hey, look, we need to have this white component, which is antiparallel, and therefore you can calculate the helicity either positive or negative. Okay. Then we said, okay, let's try to look, we've been doing this for 6 to 8 months now. This is basically looking at the top of the sample. These are the vortex, anti-vortex, you can see in green and in black. And so let's go a little bit deeper into it. What we've been doing is going to atomic resolution imaging again and looking at local displacements. These are very small displacements, you have to be incredibly careful. So I'm not showing you 90% of all of the background analysis, just to show you that indeed there's a lateral shift, which is pretty large. Anyway, it's not a big deal. In the x direction, xz plane, no problem. You see that in many different measurements. But we also see an axial shift, which is much smaller, typically about 10 to 15% of the lateral shift. Meaning, if this is my vortex, let's see if I can have a good analogy. Okay, this is good enough. There is a small component of the polarization this way, and of course there's a large component this way. And you can pick that up with this, it's about 10-15%. So we seem to believe now that there is a white component which is measurable. Theory, both ab initio and phase field are saying the same thing. By the way, the ab initio theory that they use is not classical, first principles. They call it second principles because you use model Hamiltonians. So the size of the unit cell that Javier and Jorge use is much larger. This is about 20,000 atoms, 4,000 unit cells, which is much larger than classical ab initio. Okay. All right, so we think there's reasonable reason to believe that this is the origin of the chirality in the system. Now, I'm going to speculate. This is way out there, blue sky speculation. You saw this picture early on. Those are the same boundaries. We think that across these boundaries, your handedness may be changed. We're not sure yet. We're trying to do, actually, if there are optical people who would love to have some help, we're not sure yet, but across these boundaries, the handedness is switching from that positive helicity to negative helicity. And so this is the IMAG picture of how this antiphase domain boundary. The inclined polarization component goes from this to this. What happens to the handedness? This is what we're speculating. Okay, that brings me to the last 20% of the presentation. Remember, I've been kind of signaling that this is a very complex system, and it is indeed complex. This is something goofy on the computer. I didn't even see. Okay, this is a piezo force microscopy image. Alexei will talk about the details of this, so we'll hold off on the measurement itself. And we started learning from Alexei 25 years ago. We do it quite a bit in our lab. So, but this is looking at a 16 by 16 layer superlattice. What we saw was just staggering again, because we see this very nice fiber-like organized structure. These regions have very strong in-plane piezoelectric response. These are in-plane images. Again, I think you will talk about PFM tomorrow, on Monday, where you can measure what happens to the cantilever this way, or what happens to the torquing of the cantilever in plane. So all those components can show up. So these regions, which looks like a snake surface, have in-plane polarization components like this. Uniform polarization this way, uniform this way. In between them, you have these regions which are essentially neutral contrast. Those are the vortex regions. And the vortices, keep in mind that this next scale is microns. This is about 200, 300 nanometers. The vortices are running this way. So there's a whole array of vortices. So the first question you ask is, hey, how did this happen? And the reason they happen is exactly similar to what happens in the magnetites. The two phases, the uniform polarization phase and the vortex phase, are not dramatically different in the energies. If you remember that Hamiltonian we wrote many moons ago, right now, an hour ago, that has the 4 terms. These terms are all fighting each other. And they're all approximately the same energy scale. And so you can now have coexistence of the 2 phases. Oh. So the next question is, if I have coexistence, can I go back and forth between these phases? Okay, so I'm going to show you data on that. Before that, I think there's a beautiful piece of work that one of our postdocs did. It was just, to me, very illuminating. I want to take you through that. The question was, what happens when I cool this from high temperature? It turns out that the original phase which forms is the in-plane polarized phase. And then as I keep cooling it down to room temperature, the vortex phase emerges from the uniform phase. So I can take a very small section of this section, just a small part of it. These are the white areas of vortex region. This is the vortex region. In between that is the ferroelectric in-plane polarized region. Okay. I can look at the piezo response, the phase of the in-plane response, and the amplitude. And you can see that there are domain walls in the ferroelectric phase. Not a big deal. That's why you see this contrast between black and white. But what we also saw was something which was mind-blowing in my mind, is that this contrast was going right through the vortex phase. And so there were domain walls in the vortex phase as well that we had not expected. So you can now say, hey, let me draw this boundary. That's the difference between a phase difference of approximately 180 degrees, and these are going right through. I'm going to show you a doctored image. This is the similar kind of image, but we artificially jacked up the intensity to see. This is the ferroelectric phase, and you can see these domain walls here, but in all of these, they go right through the vortex phase. So this is the first indication that we had that the vortex phase itself can have 2 different polarization vectors. There could be a domain wall in the vortex phase, and it's something that we are pursuing. So quite complicated. Okay, now comes the part where we're trying to see, can I convert this mixed phase? This is the same fibrous region that I showed you before. Mixtures of the uniform polarization and the vortex phase. What happens when I apply electric fields? A lot of things happen, and it turns out that we haven't really completely figured out everything. I'm going to show you one piece of data. When I switch it with, this is 10 volts, 15 volts negative, we can switch portions of it completely to the vortex phase. Then you say, hey, how did you know that's the vortex phase? You can go back and do micro diffraction, electron diffraction. No, sorry, X-ray diffraction. And indeed, you can pick up the structure of the vortex phase. The outer plane lattice parameter for the vortex phase is slightly larger than the ferroelectric phase because the C-axis is in plane for that. Then I can go back. At that time, we were kind of obsessed about going back to the mixed phase. And so it was an incomplete experiment. We can go back with some tricks in the writing process with the AFM. I can go back to the mixed phase. So I can go from mixed phase to uniform vortex phase back to the mixed phase. Then I can go back and I can do an X-ray diffraction. This is nano diffraction, 30 nanometer type beam size. I can pick up the structural distortions. And so this is the A1, A2, which is a ferroelectric phase, and the other one, of course, is the vortex phase. I can go back and do linearly polarized X-ray absorption studies, and indeed the vortex phase and the ferroelectric phase have different absorptions. And that you can see here for this pattern, you can see the linear absorption. I can go back and do optical measurements. This is second harmonic based measurements. Manfred talked about this yesterday in his talk. We need to do exactly the same. We work with Manfred's cousin. Marcus Raschke is at Colorado. He does all of the near field work, and so we work with him. So what you can take away, and this is important in asking the question about colossal responses, is that when you have the mixed phase, or the vortex phase is in blue, really small second harmonic response. The volume average value for the A1, A2 is out here. So it's an order of magnitude change in the second harmonic response. So this is just summarizing that the second harmonic response and the piezoelectric response. So the piezoelectric response from the ferroelectric phase is approximately an order of magnitude larger than the vortex phase. So one of the questions you can ask is, hey, why did I not see colossal responses? What does it mean? Jean-Marie was talking about yesterday, colossal. Yeah, that was GMR was taken, so when we were talking about these large responses, we talked about colossal. But it's really not colossal, it's going from 0 to 100, okay? If you flip it, it goes from 0 to infinity. So why did we not see huge responses? This is an order of magnitude change in the piezoelectric response or in the optical response. So this is speculation. We don't know the answer to that. So is this because we're now dealing essentially with a difference between bosons and fermions, or is it not that fundamental? We don't know. Lattice versus electrons. We don't understand this difference in behavior. We can get huge changes in the piezoelectric response, for example. Okay. All right. We'll finish up by going back to the vortex again. You saw this before. Looks very similar. There are pieces of this energy landscape. This is just a standard picture for a ferroelectric. There are parts of it where the curvature is negative, and so the capacitance should be negative. This ties back to what Pavel was talking about yesterday. There are regions in space where you have, and you can actually measure it. This is from the theory, of course, not experimental. This is calculated from one of the phase field calculations. And then you can map it out. So there are regions in space in the sample where the capacitance is negative, or the dielectric constant is negative. So Pavel was talking about negative capacitance in this. So we can think of this system as having, on a local basis, negative capacitance. The question is, can you measure it? And this is data, again, which Saif Salahuddin, Pavel talked about Saif's work yesterday. This guy was talking about it 10 years ago. It's now become a rage. There are people like Global Foundries and Intel actually making devices using negative capacitance. So this is the same vortex, the TEM picture, structural part of it. This is work from David Miller, where they took their data, and you can map out the local distortions, and you can map out from the electric field that we talked about, from this intervention, you can work backwards, and you can get the potential energy distribution. And from there, you could say, yeah, you could calculate regions within the vortex where the capacitance is negative. So all of them seem to agree very well. Okay, now coming to Ines' question, and then we'll finish up. We said, okay, if you remember, we started by saying I can have other degrees of freedom in this. So what happens if I now go put bismuth ferrite? The dream was, if any of you guys remember my last slide from yesterday, I said, if I can somehow fundamentally change dilution scheme, or not by changing electronic structure or something, but by somehow changing that interaction. So one of the things we were speculating yesterday was, okay, if I take my charged sublattice and rotate it by forming a vortex, will the spin sublattice follow? And it might. So if it does that, then you have a way of changing the canting angle in the bismuth ferrite system, and therefore change the magnitude of the canting moment. So we said, okay, we know how to do it with the titanate and strontium titanate, let's do it with bismuth ferrite. The answer was dramatically different. And so the answer to Ines' question, first thing we said, this is bismuth ferrite with strontium titanate. Of course, the growth here is not as easy as it is the lead titanate. We still haven't figured out how to do it well enough. It's okay at the scale, but you can see there are defects here. It is not perfect. That's the first thing. The other thing we see is you can clearly see the 71 degree domains. You can see 109 degree domains in this case. So it becomes more classical. Now, we said, let's not deal with strontium titanate, which is so different in terms of dimensions and stuff. Let's go to a known system. So this is where things went really crazy, and we're still trying to figure out. Let's take lanthanum doped bismuth ferrite. 30% of lanthanum in bismuth ferrite makes it non-ferroelectric. So it kind of looks like strontium titanate, but chemically it looks like bismuth ferrite. And when we looked at these superlattices, these were grown in Darrell Schlom's lab by MBE, perhaps the best that we can grow so far. What we saw was something which was unexpected. We were expecting domain formation. Instead, the bismuth ferrite, the lanthanum doped bismuth ferrite did nothing. And by the way, there's no chemical interdiffusion, it's all pretty okay. The bismuth ferrite went into an antiferroelectric phase, which we did not expect at all. And you can see these arrays of antiferroelectric phases everywhere. And that's the atomic structure of the antiferroelectric phase. You can see that it looks very much like the lead zirconate type structure. And the distortions are given by these arrows that go up, down, up, down. So somehow, I think a lot of credit to Jorge, if he was here, he deserves credit, because when the original work from Nicola, and you guys should ask Nicola this question when she talks on Monday, there was a very strong focus, of course, on the polar phase and the antiferromagnetic phase. But Jorge kept on saying, guys, there's a whole bunch of phases in the system that we need to be thinking about. You know, there's a lot of phases with almost the same energy. And one of them is the antiferroelectric structure in the system. So this is where we are. We don't understand this whole business completely, but it's another example of something that we expected something, but the system went totally different. Okay, to summarize, what I hope you have taken away from this is that first, you can make these kinds of artificial superlattices like our semiconductor colleagues can. You know, the reason fractional quantum Hall effect happened is because Art Gossard and Lord Pfeiffer could grow fantastic gallium arsenide algas superlattices by MBE. Yeah. Those guys did not win the Nobel Prize because they're not physicists, okay, yippee, whatever. But the entire physics was enabled by the fact that you can grow these highly perfect materials, in their case with electronic properties, mobilities of 50 million. So that's the first one. I hope you can take away that indeed these are vortices. They are not an artifact of the electron microscopy process. We can measure them in many different ways. They have significantly different properties. We focused a lot on their handedness, their chirality. And the chirality, to finish up with Vincent's question, is emerging because of the in-plane component of the polarization, which is really critical. We think, not completely sure yet, but think that the handedness is electrically controllable, which is pretty interesting. I also showed you data on phase coexistence, which again, you could think of this as a kind of a rational way to design a Manganite type system. Manganite was an accident. We were looking for something totally different. We ended up with something which showed very large magnetoresistance. So we can start to design these. We don't understand much about the dynamics of these vortices, just because we haven't really gone deep into it. And I finished up by saying, hey, can we do the same thing with spin systems? I think there's a huge opportunity here. I think it starts by growing these guys well enough. I don't think we're there yet. And of course, we ended with this question yesterday. We will end with the same question: is can you now start to control these interactions at the microscopic scale by playing games with the topology of this? So with that, we'll stop, take questions.